I decided to do one more day of notes for Unit 7 to practice some AP style questions. So the questions that we're going to go over today on our notes are all from previous AP exams. Okay? On your test in my class, you will have 2 of these FRQ AP problems. Not these particular ones, but other AP problems. Okay? So I wanted to give you some practice and some tips. Now on my test, both of these will be, you'll be able to use a calculator on them. Okay? So I'd like to, I gave you some notes, and this is your number 1 in your notes packet over this material. And the 3 that are in your notes packet are all with a calculator. Okay? So let's practice what this will be like. Okay, so this first one was back from 2008. This was number 1, so it was with a calculator. And they say, let R be the region bounded by the graphs of y equals sine of pi x and y equals x cubed minus 4x as shown in the figure. Okay? Now I'm going to tell you, they will often do this where they give you the graphs, or the graph, okay? And they give you the equations, or they explain, they'll always explain what's going on with words, what's going on with the graph. Even though they give you this graph, you're still going to need to put these equations into your calculator. Alright? So I'm going to begin by going to my calculator. You guys go to your calculator, and we're going to put these into our y equals. So for y1, I'm going to put the sine of pi x. And for y2, I'm putting x cubed minus 4x. Now, double check this and make sure that you put it in correctly. Because if you don't put it in correctly, every answer will be wrong. And you don't want that to happen. Okay? And there's nothing I can do about that if every answer is wrong. You just can't get those points. Okay? All right. So we will need to see, I'm going to graph this so that this picture kind of shows up on my screen so that I know that I graphed it right, or that's further confirmation that I put it in right. So in my window, I'm going to do my window similar to what the numbers are here. So for x, I'm going to go from 0 to 2 for x. 0 to 2 for x. And for y, it looks like they went from -3 to 1, so I'm going to go from -3 to 1. Okay? So let's graph that. There's the sine curve. And there's the cubic, part of the cubic curve. Now I see that it looks like this is down at -3, but it must go down a little bit further than -3. Okay? Unless I graphed it wrong, and I'm pretty sure that I graphed it correctly. So just know that this point down here is not y is equal to -3 if we need that. If we have to find that low point, we'll have to go find it on our calculator. Okay? All right, part A says to find the area of R. Find the area of R. So, to find this area, we know how to find the area. It's an integral from 0 to 2. I can do from 0 to 2 because the same curve is always on top and the same curve is always on the bottom. So this is not too bad. We can do the integral from 0 to 2 of just the top minus the bottom, right? Top minus bottom. So that will be my sine of pi x minus the x cubed minus 4x dx. And that can go in our calculator. And another good thing about having these functions in for y1 and y2 is now we can use those and we don't have to keep retyping this in, right? So math 9, 0 to 2 of y1 minus y2. Remember, to get the y1 and y2, we go to that little f4 there. So alpha trace will give you the f4. And that turns out just to be 4. That was a little surprising. Doesn't look like it would be 4. All right. Part B. The horizontal line y equals -2 splits the region R into 2 equal parts. Or not 2 equal parts, 2 parts. Okay, so where is y equals -2? Well, y equals -2 is about right here, right? There's y equals -2. And yes, it does split region R into 2 parts, not 2 equal parts, but 2 parts. Write but do not evaluate an integral expression for the area of the part of R that is below this horizontal line. So we want this area. So we can find that area. It's just what's on top, integral, what's on top minus what's on the bottom. All we need to do is find these intersection points because those are going to be the boundaries of our integral, right? So back to our calculator, y equals, in for y3, I'm going to put y equals -2. And we'll go graph that. Okay? We need to find these intersection points. So second calc, 5 for intersection. Now notice up right now we're automatically on the very first curve. We're automatically on y1. We don't want y1 for this part of the problem. So we only care about y2 and 3, right? So go down to y2 or y3. I'm going to get close over here to this one. Enter. And now the other one is y3, so enter and then guess. So that intersection point down there is given right here. You want to write this down. So I'm going to say intersection points. We're going to have 2 of them. X equals 0.5391 blah blah blah. And we really don't, I'm not going to write what y is because I already know what y is, right? Now, I'm going to need that for my integral, right? So what I'm going to do is say equals a. And then I need to always tell AP what you're doing. Don't just do a bunch of work on your calculator and go spit a number out. It won't be enough. You won't get the points. Okay, so I'm going to go store this value in for A. So let's see what I do to do that. I'm going to go to my home screen. Right now, stored in for X is that 0.5391. That's in there right now. The calculator thinks that's X. It'll lose it though as soon as I trace something else on my graph. It'll think something else is X, and I don't want to lose that. So I'm going to store that X value in for A, alpha A there. Enter. So now that's stored in for A, and that won't change until I change it. Okay? But X is going to change. Let's go get that other intersection point. So now we want this intersection point. So I'm going to, again, right now we're on y1, so I'm going to go down to, I think I'm going to go down to y3. It'll make it a little bit faster to get over there. Okay, I'm going to enter. Now, I don't want y1. I want y2. So there's that X value. And X equals 1.6751 blah blah blah. Okay, and I don't want to lose that either, so I'm going to go and store that. I'm going to tell AP what I'm doing. I'm going to store that in for B. So back to my home screen. Now X is something else. It's that new number, and we're going to store that in for B. And now I won't lose that until I change it. Okay? Alright, so this write but do not evaluate the integral expression for the area, the integral expression will be integral a to b. I don't have to rewrite the decimals because I can just use the a and b of what's on top is -2 minus what's on bottom is the x cubed minus 4x dx. And that is the area for the part of the region that we're trying to find the area of. Okay? All right. Part C. Region R is now the base of a solid. So we're back to the entire region R, and it's the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a square. Find the volume of this solid. Okay? So for these types, we took the same distance and we called it S each time. Remember? We called that S each time. But it's the same top minus bottom, right? So S will be sine of pi x minus the x cubed minus 4x. That's just S. The volume will be, we want each cross section to be a square. So remember, volume is the integral 0 to 2, because we're perpendicular to the x-axis, of the area. And the area of a square is s squared, right? So this will be S squared dx. Now, since I already named S, I could have just written the letter S here. S squared dx. And actually, well, I don't want to use A here because I already used A, so that might be a little confusing. Although this A would override the previous A. But then we can't go back and use that if we need to later. We have to rename it. Anyway, I'm going to just write that. And now it says to actually find. Up here it said to write but do not evaluate the integral. So we got to stop there. We could have very easily found it, but we didn't have to. Here it says to find the volume. So we need a number. Find the volume means write the number. Write but do not evaluate an expression means you can stop. Okay? All right. So back to our calculator. Math 9, 0 to 2. That's y1. Whoops. No. Let's go back. Alpha F4. I did second F4. Or second trace. Okay. y1 minus y2 dx. Oh, I didn't square it. Just now I forgot to square it, right? I did not square that. So let's go back and square that. y1 minus y2 squared dx, and we get 9.978 if we round to 3 decimal places. Remember, at least 3 decimal places, at least. Okay. Part D. The region R models the surface of a small pond. Okay. At all points R in R, at a distance x from the y-axis, the depth of the water is given by h of x is equal to 3 minus x. Find the volume of the water. So this is now the surface of a pond. the surface of a pond, and it has depth, but the depth changes depending on how far away from the y-axis you get. So let's just say at this distance from the y-axis, the depth is 3 minus x, right? And since they say the depth is like that, it's like it's a rectangle where the depth is just 3 minus x the whole way down. It doesn't curve like I had it down there. It goes all the way down straight. It's a weird pond. Okay. All right. So remember that volume is always area times dx, right? Or area times dy, but in this case we're definitely going to have x's. So area times dx. So what is the area of this little rectangle? Well, it's our old s, right? Top minus bottom, times the depth, 3 minus x. So this volume will be the integral of 0 to 2 of that s sine of pi x minus x cubed minus 4x. That's the length, and now we need the depth, 3 minus x dx. For the sake of your notes, remember that this is just area of a rectangle. And then giving it a little thickness allows us to find the volume. Okay? So we have to actually find this, so we will find it. Math 9, 0 to 2. Okay. Let's see, parentheses. I need y1 minus y2 again. That's a good one to put in our calculator, actually. y1 minus y2. We use that a lot. Times 3 minus x. I think I'll do that in the next problem. dx. So we got 8.370 would be rounded. Remember, at least 3 decimal places. You can give more, but don't give fewer. Okay. Number 2. Take a look at number 2 on your sheet. Okay. In number 2, this one was from 2007. It was with a calculator. It says, let R be the region in the first and second quadrants, bounded above by the graph of this, and below by the horizontal line y is equal to 2. So again, let's go and get a picture of what's happening here. So let's go to our calculator, clear out what's there. So we need to put 20 divided by, don't forget parentheses around that denominator. And then we're bounded below by the line y is equal to 2, so I'm going to put 2 in there. Okay? And I'm not sure what this graph is going to look like. I could do a little work here to figure it out, but I think I'm just going to do zoom 4, and that'll just give me a general graph here. Okay, well, I need to see what's happening above that. Do you agree? So when x is 0, what is y? 20. So on my window, I'm going to come down and do my y max at 20. Or maybe 21, just to see a little bit above that y max. Okay, that's better. Now I get a clearer picture of what's going on. I can see the region, right? And we can deal with that. Now for me, just for my notes, and you never have to sketch a graph, but I'm going to sketch this graph just for the note's sake. So this is 2 right here. And this is up here is 20. Okay? All right. Part A, find the area of R. So just the area of this. Integral, top minus bottom. No squares, no nothing, just integral, top minus bottom. So the integral of the top minus the bottom, so that's going to be my 20 over 1 plus x squared minus the bottom is 2 dx. All I need to do is get some boundaries here. So back to our calculator we go, and let's find the intersection points. Second Calc 5. I'm going to go over a hair. Enter, 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 and there certainly appears to be some symmetry here, and looking at the equation I can tell that there is symmetry there. So we get 3, x is 3 at that intersection point. So this will be 3 and negative 3, so my integral will need to go from negative 3 to 3. And this time I am going to, you guys, since we used it so much last time, I'm in for y3. I'm going to put y1, oops, I did it again, y1 minus y2. And I don't want to see that graph, I just want to be able to use that function on my home screen. If you don't want to actually see the graph, push enter on that equal to sign, and you can use this function without viewing the function, okay? So over here on my home screen, I'm going to do math 9, negative 3 to 3. I have pushed enter too soon, sorry. Of, now this is y3, okay? So y3 dx. So that ends up being 37.962, like that. Okay, part B. Find the volume of the solid generated when R is rotated about the x-axis. X-axis. Big R, little r, right? Big R will be top minus bottom. So that's just our 20 over 1 plus x squared, y1. That's our y1. Little r is 2 minus 0, so little r is just 2. So the volume will be the integral from negative 3 to 3, because those are our boundaries, pi times big R squared, pi r squared, minus pi r squared. Because each cross section here is a circle, right? That's how we got that. So back to our calculator. Math 9, negative 3 to 3, pi times y1 squared, right, minus pi, not e, pi times 2 squared, or 4, okay, dx. Wow, that's a big area. 1,871.190. At least 3 decimal places. At least 3 decimal places. All right. Now it says region R is now the base of a solid. Okay. So we're no longer revolving. It's just the base of a solid. For this solid, the cross sections perpendicular to the x-axis are semicircles. We know the area of a semicircle, right? Pi over 8 s squared, right? Find the volume of the solid. S will be, so S is the same that we use for the top minus bottom. That's our S, right? That's the side, or in this case the diameter of our semicircle. So S for us is just that top minus bottom. We use that a lot in these problems, right? So the volume will be the integral from -3 to 3 of pi over 8 times s squared. That's our formula for the area of a semicircle in terms of the diameter. Okay, so math 9, -3 to 3, pi over 8, times, this is our y3, right? That's my y3. So alpha y3 squared dx. And we get 174.268. 174.268. Okay? And that's our problem. Okay, number 3, our last one here. This was back from 2006. Again, number 1 with the calculator. Let R be the shaded region bounded by the graph of y is equal to ln of x and y is equal to x minus 2. So yes, they gave the picture, but you still need to go and graph it yourself. I guarantee you'll need to do that. So let's go back to our y equals, clear out what's there. I think I'm gonna leave that in there though, because that's a useful thing. And for y1, I'm putting ln of x, natural log x. And for y2, I'm putting x minus 2. And to graph it, I want a good picture, and they didn't put any units here, so I don't know what the units are. So I'm just going to zoom. Whenever I don't know, I just zoom 4. If I don't know, I zoom 4. And it turns out that's pretty decent. I think I'm just going to leave it like that, because I can live with that. Okay? Can totally see what I need from that. Okay, so first of all, find the area of R. Have you noticed a trend? Find the area of R. Find the area of R. What was number 1? Find the area of R. A little bit of a trend there. They like those questions first. Okay, for R, again, we use what we call S, that length, right? Top minus bottom. So the area of R will be the integral. Oh, here I need my boundaries. I already need my boundaries. So let's go get these intersection points. So second calc 5. I need to go over a little bit because if you just do enter right there, you're not going to get anything. So my first intersection point is this. Now, in this problem, I don't know if I'm going to need that y intersection point. Do you see what I mean? There's a chance I'll need that y intersection point. Okay, so here's what I'm going to say, and here's what I'm going to do. Okay, I need to tell AP what I'm doing here. So I'm going to say intersection points. I'm going to let A equal the point 15859 ... And I'm going to let C, because it's a y value, equal -1.8414 ... Okay? So before I lose these two values, let's go store them. So go to your home screen, store the current x value, stow, in for A. There it is. The current y value, so go grab y. The current y value, stow, in for C. There it is. So A and C will not change until I change them in my calculator. X and Y will change. As soon as I trace to another point, X and Y will change. So those will change, the calculator values will change as you move your screen on your graph. But the A and C and all the other letters will stay what they are until you're ready to change them yourself. Okay, we need this other intersection point. So second calc 5, let's go over a little bit, get a little closer, and then enter, enter, enter. Okay, so I'm going to say B is equal to, okay, B is equal to 3.14619, is that pi? No, it's not pi. And then I'm going to call this next one D for my y value, my y intersection of the y coordinate there. There we go. So let's go do that. So second quit. The current x value, store it in for B. The current y value, store it in for D. And now we have all those intersection points, and we're not going to lose them, right? Okay. So my area of R here, let me pull back my little sketch. My area of R will be, since I'm doing top minus bottom, I'm using my X intersection points, right? So A to B of the top minus the bottom dx, right? And remember, the top minus the bottom is stored in for my y3, right? So math 9, A to B, because we stored those values in, of y3 dx. So 1.949. Okay. Part B. Find the volume of the solid generated when R is rotated about the horizontal line y equals -3. Y equals -3. So since this y value is -1.8, y equals -3 will be below here, right? There's y equals -3. And we want to revolve or rotate R about that line. So I need my big R, and I need my little r, right? My big R will be top minus bottom, that's my natural log x, right? Natural log x minus a -3. Minus a -3. Little r is the line minus a -3. So x minus 2 minus a -3. Okay? So my volume will be integral. We're doing still a delta x here because each of these has a little delta x thickness. So A to B still, right? And then pi times big R squared minus pi times little r squared dx, right? Pi r squared, area of the circle. Math 9, A to B, pi times, and it'd be just as easy to put ln x plus 3 squared, make sure you type it in right, minus pi times x plus 1 squared dx. 34.199. Remember, at least 3 decimal places. You're welcome to give more, but if you give fewer, your answer will not be correct. It has to be correct to 3 decimal places. They actually allow you to truncate which means just give the first three that are shown regardless of what comes next. That's called truncating. So they would also take 34.198 here. All right? Write but do not evaluate, so we don't have to use our calculator. An integral expression that can be found to find the volume of the solid generated when R is rotated about the y-axis. Okay, so now we're going to revolve it around the y-axis. I would choose to use the cylindrical shell method here. We can certainly use either, but I'm going to use the cylindrical shell method. So there's my slice. When I rotate it, there's my cylinder. This is the height, right? This is the radius, yes? So the volume will be the integral from A to B still, right? Of 2 pi R. What is R? In this case, R is just x, because x is always from the y-axis to your slice, and that's exactly what R is here. 2 pi RH. H is top minus bottom. That's our ln x minus the x minus 2 dx. And that's it. If we had chosen to use discs and the washers for that one, you guys, then we would have used the 2 y coordinates up here. We would have had to, because it would have been a dy instead of a dx. We would have solved each of these for x, and then used the c and the d here. Okay? Alright, so that's it on using your calculator on FRQ problems. It gives you a little bit of an idea about what an AP question along these topics would be like too. All right, I did give you some in your worksheet, so go and try some on your worksheet. Go practice.